right, this is the fifth lecture from chapter 10, Chemical Reactions. And I told you there was a lot of math in this one, and here's the heavy duty type of math. So the section is talking about Avogadro's number, and Avogadro's number is tied to the mole. So way back at this beginning of the semester, I told you one of the metric units in measurement is the mole. Not the little critter, but the mole is talking about the number of atoms or molecules in a unit. So the mole is equal to, as you can see here, 6.02 times 10 to the 23rd atoms or molecules. So I won't ask you to do any super complicated math with this exponent, but you should know what a mole is. So 1 mole equals this 6.02 times 10 to the 23rd. So think about that. That means you would move this decimal point 2 times and then add 21 zeros after it. That's how many atoms or molecules we're talking about in this unit. So what are we talking about? Well, Avogadro's number is going to relate the mass of a material to the number of molecules. So the atomic mass of an element, this is where the periodic table gets even cooler, or the mass of a molecule in grams is equal to 1 mole of that element or molecule. So if you think about that for a second, that's actually really cool. The atomic mass of an element or molecule in grams is equal to 1 mole of that element or molecule. So let's take a look at what we're talking about. So if we look at the periodic table, there's our little mole. So remember 6.02 times 10 to the 23rd. So what we're looking at as far as the mole is this. So if you look at your periodic table and look at helium, helium's atomic mass is going to be 4.00. Oh, on ours it's 4.0026. So they've rounded theirs to 4.003. So if we had 1 mole of helium, meaning that we had 6.02 times 10 to the 23rd atoms, or 602 with 21 zeros after it, atoms of helium, that means it would weigh 4.003 grams. So this atomic mass that you find on the periodic table is equal to 1 mole if you add grams after that number instead of AMU like we've been using so far. So if you look, they've done it for lead. So lead, its atomic mass is 207.2 approximately, which means that 1 mole is equal to 207.2 grams. So if you measured out 207.2 grams, you would have 1 mole, or 6.02 times 10 to the 23rd atoms. Same thing for sodium. 22.99 is going to get you 1 mole. So this is really helpful when we get into looking at things like equations, because it works for compounds as well. So we can do hydrogen. So hydrogen is 1, right? It's got an atomic mass of 1. And so what we can do, if we've got it in an equation like this, okay, so it's got an atomic mass of 1. We've got 2 times 2, we've got 4 of them, right? So this 2 up here is actually equal to 2 moles. Make sense? So the coefficients are equal to the number of moles that we need of that element or compound. So 2 moles, we know that there are 2 atoms of that element. So that means it's going to be, they've already done the math for us, but that's going to be 2 moles times 2 grams, because we know that hydrogen is 1 gram according to the periodic table, times 2 because we've got that subscript. So 2 moles times 2 grams is going to get us 4 grams. So 4 grams of hydrogen is going to be 12.02 times 10 to the 23rd molecules, because we're looking at 2 moles. So 2 moles of it is going to multiply the 6.02 times 10 to the 23rd. You're going to have twice as many molecules, or atoms, depending on who you're looking at. We're looking at molecules here because it's H2. So you just take the number of moles and multiply it by this number, the 6.02 times 10 to the 23rd, to get your number of molecules. Here we've got O2. So we wouldn't have the one here, but we assume it. So they've written it in. So since there's just one, that means we have 1 mole. 1 mole means we have 6.02 times 10 to the 23rd molecules. Cool. We have 1 mole and we have O2, which means that we're multiplying 1 mole times 2 times 16. Because remember, oxygen has an atomic number of 16. Again, you can always look it up if you don't know it. I've been doing this for a while, so I remember a lot of these numbers. So 1 times 2 times 16 gets us our 32 grams. So 32 grams of oxygen is going to be our 1 mole, 6.02 times 23. Now we can do a compound. So we've got hydrogen, H2, and oxygen to make our water. We know we have 2 moles because we've got a coefficient of 2 in front. So we know hydrogen is 1. We've got 2 of them, so we have to multiply it by 2. And then we have to add 16. Right? So we've got 16, 17, 18 times our 2. And that gets us 36. 2 moles, again, you multiply 6.02 times 2, you get 12.04 times 10 to the 23rd. So you might be going, wait, these don't equal. They do, because remember, these guys aren't combined yet. It's the same number. Yeah, we've got 12.02 or 12.04 molecules, but these are talking about molecules, not atoms, right? So that's the difference. Now, the other cool thing is what's happening, because of the mass. If you look on this side, we've got 32 plus 4. That gets us 36. Okay? This is one of the ways you can also check to make sure that your equations are balanced. So let's take a swing at this and practice as far as Avogadro's number. So how many molecules are in 44.09 or 009 grams of carbon dioxide? How would we figure this out? Well, the first thing we need to figure out is what is the mass of carbon dioxide. So carbon is 14. Let's see. No, sorry. I've got the wrong one. That's nitrogen. Erase. So carbon is 12.011. And we're going to add that to oxygen. So that's 16. Now that's times 2, right? Because we've got 2 oxygens. So 16 times 2 is, sorry, my brain shorted out there for a second. 16 times 2 is 32, and we add that to our 12.001, which is going to get us 44.001 or 0.011, which is pretty close to our value here. I just rounded up because this is actually 15.999. So we're pretty close, which means that we have in this answer 1 mole of carbon dioxide, which is going to give us 6.02 times 10 to the 23rd. Okay, so let's take a look at another one. So 63.996 grams of oxygen. So you can tell this got a big decimal, so they didn't round it. So oxygen is 15.99 grams. So how do we figure it out? You're going to take the original number and you're going to divide. So it's definitely too late in the day for me to do that in my head. Haha, yeah, I definitely can't do that one in my head. So that, if you take 63.996 and divide it by 15.99, that is going to get you 4. If you keep going, it's 4.002. Close enough. So we're going to go with 4 moles. So then what you're going to do is take that and multiply it by our Avogadro's number, 6.02. So that's going to give us 24.09 times 10 to the 23rd. It's okay if you write it this way. Technically, you should move the decimal point and do it as 2.409 times 10 to the 24th. I would accept either answer. Okay. So let's take a look at another problem. So this one, sometimes when people see this, they're like, I have no idea what to do with that. You've just given me a formula. How am I supposed to figure out how many molecules are in that? Well, take a second and think about what you see. So when you see a formula, what is assumed about a formula like this? The assumption is that there is a 1 in front of it. And when we're looking for moles and molecules, we're looking for the coefficient. And so the coefficient here is 1. So 1 mole is equal to 6.0. I'm getting really bad at writing with this. 2 times 10 to the 23rd. Okay. So I believe I have one more. Yep, one more. So for H2O, so this is from an equation. So same thing, it's got a coefficient. So the coefficient tells you how many moles you've got. So you're going to take that and multiply it by Avogadro's number. So this is going to end this lecture. We've got one more lecture working with things like Avogadro's number and atomic mass and regular mass.